So in this video lesson, we're going to have a look at calculating the Mach number, and we're going to look at the Doppler effect. So Mach number you might have heard of if you've ever watched Top Gun or any type of movie where we are dealing with fighter jets. And they're always talking about aircraft going Mach 2 or Mach 3 or Mach 4. And so Mach number is just a relative speed of the airspeed around the object. So like the airplane or fighter jet, anything like that, and the local speed of sound. So Mach number is actually represented by a big capital M. And it's going to be airspeed of your object. So that would be like how fast the plane is going. But it doesn't have to be a plane. It could be another object. Just the things like airplanes tend to travel pretty fast through the air over our local speed of sound. And I want to remind you that that local speed of sound is dependent on temperature. Okay, so we're using our regular equation to calculate the local speed of sound based on our temperature. Mach number is going to have no units. And so what that means is that the airspeed and the local speed have to be in the same units. So they really should both be in meters per second. But you could actually use any other units you want to, as long as both of those speeds are in the same unit. All right, so we are going to do a practice. I think we're going to do 2 practice questions with Mach number. Oh, practice number 1, not number 2 yet. All right, so our speed of sound is 344 meters per second, so giving us the speed of sound to start with. And the speed of our aircraft is 910 kilometers per hour. And we want to try and find the Mach number. So the first thing that we want to do is we need to turn that 910 kilometers per hour into a speed in meters per second. So 910 kilometers per hour, we're using our unit conversions. There's 1,000 meters in 1 kilometer. And then 1 hour is going to be our 60 minutes. And 1 minute is going to be our 60 seconds. All right, so we're doing 910. We're multiplying it by 1,000. We're dividing it by 60 and then dividing by 60 again. So that gives us a speed of 252.8 meters per second for our aircraft. So our Mach number is going to be the speed of our aircraft, 252.8, over our local speed of sound, which is 344. So 252.8 divided by 344. So we're getting a Mach number of 0.73. So no units for our Mach number. Okay, so then let's try a second example where we have Mach number. And let's use this to try and find our temperature. So practice number 2, we know that the Mach number is 0.93, and we know the speed of our airplane is 3.0 times 10 to the 2 meters per second. And we're trying to find, let's actually say that we're trying to find the temperature. So in order to find the temperature, we're going to need to find the local speed of sound. So our Mach number, 0.93, will be equal to the speed of our airplane, 3.0 times 10 to the 2, over our local speed of sound. And so we're just going to rearrange that. Which means our speed of sound is going to be 3.0 times 10 to the 2 divided by our 0.93. that means our local speed of sound is 322.6 meters per second, okay? And so then we're going to use this to find our temperature. And so we know that the speed of sound is 331.4 plus 0.606 times our temperature. So if we know that the speed of sound is 322.6, it'll equal 331.4 plus our 0.606 temperature. And we're just going to rearrange to find our temperature. Okay, so 322.6 minus our 331.4. So we've got negative 8.8 is equal to our 0.606 T. So we're going to divide by 0.606. So that means our temperature is negative 14 degrees Celsius. Since we're dealing with an airplane, that actually makes quite a bit of sense because the airplane is probably relatively high up in the air. And so it's definitely probably not very warm up there. All right, so that's it for Mach number. We can just use the Mach number equation to help us calculate either the speed of an aircraft or the Mach number, or we can use it to even calculate the local speed of sound, and that can help us to find our temperature. So we're going to move on to the Doppler effect. And the Doppler effect is going to, it's essentially how we hear sounds. So it's how we hear sounds when they're moving either towards or away from us. Or if we happen to be moving towards or away from a sound. So for example, if an ambulance drives by, so if you're sitting in your home and you hear an ambulance drive by, you can actually tell based on the sound, and specifically it's going to be the sound frequency, whether the ambulance is actually coming towards you or moving away from you, okay? And so what happens is that if the distance is decreasing, so that means we're moving towards the sound, then we end up hearing a higher frequency than the one produced. So if the ambulance is moving towards you, or if you're moving towards the ambulance, you are decreasing your distance between you and the ambulance. And it doesn't have to be an ambulance, it just could be anything that's making sound. You are going to actually hear it at a higher frequency than the frequency it's producing. If the distance is increasing, which means we're moving away, so again, whether you're moving away from the sound or the sound is moving away from you, we're going to hear it as a lower frequency than the one produced. So depending on whether you hear a higher frequency or a lower frequency, it's going to depend on whether the object is moving towards you or moving away from you. And the formula for our Doppler effect is actually on your formula sheet, so you don't have to memorize it. But this is what the formula looks like. So the frequency that is detected or heard is the frequency made or produced times the speed of sound over the speed of sound plus or minus the speed of your object. Okay, now the tricky parts for this formula is really this section in here. So if you have an increasing distance, so increasing distance, that is where you are going to use a positive sign. And if you have a decreasing distance, then that's where you're going to use a negative sign. So depending on the situation that you're dealing with, that's where you choose whether you're using a positive sign there or whether you're using a negative sign. Okay, and so increasing distance we know is going to be meaning moving away. And a decreasing distance we know is going to be moving towards, okay? And so at the beginning of Doppler effect problems, you really want to double check and make sure, are you increasing your distance, so are you moving away, or are you decreasing your distance? Are you happen to be moving towards the sound? Okay, so we are going to do some practice here with the Doppler effect. Okay, so a police car is approaching at 20.0 meters per second with its siren. Pen doesn't want to write as fast as I do. Emitting a frequency of 1.0 kilohertz. What frequency does a stationary observer hear? And we're given the speed of sound in this case. So they gave us the speed of sound was 330 meters per second. Okay, so in this problem, we have a couple of different things. So we're given that speed of sound, so that's great. We don't have to calculate that. You might have to calculate that based on temperature, but in this case, we don't have to. We know that the siren is producing that frequency of 1 kilohertz. So that means the frequency produced or made is 1.0 kilohertz, which is 1,000 hertz. We know the speed of our car is the object, and so that's going 20 meters per second. And we know the speed of sound is our 330 meters per second. So we are going to try and calculate the frequency detected by using our frequency produced, so that's 1,000 kilohertz. And then we're multiplying that by our speed of sound goes on the top, 330. And then on the bottom, we're using our 330. And whether we're going to add or subtract the speed of the car is dependent on whether we're moving away or towards. So it says that this police car is approaching us, which means we're moving towards, and that means we are going to subtract. So we've got subtract our 20 meters per second. Okay, so we're gonna leave our 1,000 here for a minute, and we're gonna do this division. So 330 divided by our 330 minus our 20 is gonna give us a total of 1.06. So then we're going to times that by 1,000. So we get 1,064 hertz. And we should give two significant figures there. So we're going to round up to 1,100 hertz. All right, let's try another practice question. So let's try practice number 2. Okay. So in this one, we're going to be looking at an ambulance, and the frequency that you detect from the ambulance is 900 hertz. The frequency that's produced by the ambulance is 950 hertz, 950.0 hertz. And our speed of sound, in this case, is going to be 335 meters per second. And that means that since we're dealing with a frequency that we've detected that is lower, I just want to remind you what that means. So a lower detected frequency than the one produced means that we're moving away. Moving away is going to mean we're going to use a positive sign in our formula. So our frequency detected is going to be our 900 hertz. Our frequency produced is our 950 hertz. And then we're multiplying by the speed of sound, which is 335. Over our speed of sound, we're going to add the speed of our ambulance. And so the speed of our ambulance is what we're trying to solve for. All right, so the first thing we're going to do is we're going to move that 950 to the other side by dividing. So 900 divided by 950 gives us 0.947. So that's going to be 335 over our 335 plus the speed of our ambulance. And I'm just going to shorten that to a VA so that we don't have to keep writing ambulance every time. And then we need to cross multiply there. So 0.947 times 335 plus VA is going to equal 335. So then we're going to have to distribute through those brackets. So 0.947 times 335 is 317.2. Plus now we'll have 0.947 VA is equal to 335. So we're going to move our 317 to the other side. So it's going to be subtracted on the other side. So 0.947 VA is going to equal our 335 minus our 317. So 17.8. And then we're just going to divide both sides by 0.947. So we're going to hit 18.8. And that's going to be in meters per second. That's the speed. So then that's the speed of our ambulance, 18.8 meters per second. So the biggest tricks in doing these Doppler effect questions is making sure whether you know whether your object is moving towards you or away from you, and whether to use a positive sign or a negative sign in your equation. And that's just going all the way back to if we're increasing our distance, so we're moving away, we're going to use a positive sign. If we're decreasing our distance, we're moving towards, that means we're going to use a negative sign. And unfortunately, we just need to memorize those two situations. So when we use a positive sign and when we use a negative sign. And that's it for the Doppler effect.